Swayam Prabha. Digital India. Educated India.
Hello student, welcome back to the course on optimization methods for civil engineering. So today we will solve few problems using NSGA II algorithms. We will solve 4 multi-objective optimization problems here, 2 problem without constraint, that means unconstrained multi-objective optimization problem, and 2 with constraints. So let us see the 4 problems. The first problem, we have 2 objective functions. So both are minimization type. So you can see f1 equal to x and f2 equal to 1 plus y square minus x minus a sin b pi x. So we have considered a equal to 0.2 and b equal to 1, and range for x and y, x is between 0 and 1 and y is between minus 2 and plus 2. So, y is varying between minus 2 and plus 2. So, range of y is minus 2 and plus 2, and range of x is 0 and 1. So, if I solve this problem using NSGA II, so I should get this Pareto optimal form. So, here in the x axis we have objective function 1 and y axis objective function 2, and I should get this Pareto optimal form. The second problem has 3 objective functions. So, all of them are minimization type. So, you can see that f1 is 0.5 x square plus y square plus sine within bracket x square plus y square, and objective function 2 is thrice x minus twice y plus 4 whole square divided by 8 plus x minus y minus 1 whole square divided by 27 plus 15, and there are another objective function, that is f3, and that is 1 by x square plus y square plus 1 minus 1.1 exp minus of x square plus y square. Okay. And the range for x and y is minus 3 to plus 3, that means x is between minus 3 and plus 3, and y is also between minus 3 and plus 3. So, if I plot these 3 objective function, and I should get this Pareto optimal form. So, this is in the x axis it is f1, then y axis this is f2, and z axis f3. So, I should get this Pareto optimal form. So, NSGA can solve more than 3 objectives. Okay. So, we can have 4th objective function, 5th objective function like that, but here we have shown up to the 3rd one, so that we can plot it. So, this is the Pareto optimal form for this particular problem. Then the 3rd problem is a constraint multi-objective optimization problem. So, you can see that it is a minimization type function that minimize f1 equal to x and f2 equal to 1 plus y by x, and range for x1 is between 0.1 and 1, that means x is between 0.1 and 1 and y is between 0 and 5. So, it has 2 constraints g1 and g2. So, you can see g1 equal to y plus 9 x, it is a greater than equality type constraint. So, y plus 9 x greater than 6, and g2 is minus y plus 9 x greater than equal to 1. Okay. And as I said, that range for x1 is 0.1 and 1, and that for y is 0 and 5. So, I have solved this problem with constraint and without constraint. So, you can see that first graph. So, whatever I have shown here. So, this is without constraint, that means I have solved this problem using NSGA II, and I should get this Pareto optimal form. And if I use this constraint, that is g1 and g2, and you should get this particular Pareto optimal form. So, when we are using NSGA, so you note that the objective function should be minimization type for the package we are using in R. So, objective function should be minimization type, that means minimize. So, anyway, so I can convert a minimization problem to maximization problem or maximization problem to minimization problem, but in this particular package. So, we should use minimization type, that means if you have a maximization type problem, then I should multiply it by -1 and convert it to minimization type. Similarly, the constraint should be greater than equality type. Okay. So, in this case this is y plus 9x greater than 6, and similarly z2 equal to minus y plus 9x greater than equal to 1. So, as I said that for this particular package that we will use in R, so it can take greater than equality type. So, therefore, I will write this constraint like this: y plus 9x minus 6 greater than equal to 0, and similarly this one I will write minus y plus 9x minus 1 greater than equal to 0. So, therefore, so this is your z1 and this value is your z2. So, we will do that one. So, I will use z1 and z2 like that. So, if we solve this problem, as I said that this is unconstrained multi-objective optimization problem, then I should get this particular Pareto optimal form, and when we are using these two constraints, so we should get this particular Pareto optimal form. So, this is your problem 3. So, now we have another problem, that is problem 4, and this is also a minimization type optimization problem. So, minimize f1 equal to x and f2 equal to 1 plus y exp within bracket minus x by 1 plus y. So, this is objective function 2, and then we have two constraints. The constraints are this is f2 divided by 0.858 exp minus 0.541 f1 x1. So, that means in the to calculate constraint 1. So, I have to calculate first f2 and f1, and it is greater than equal to type, and similarly the z2, that is the second constraint, is f2 x y, f2 x and y, this is 0.728 exp minus 0.295 f1, it is also greater than equality type. So, what I will do basically, so as I said that I will convert it. So, I will put this is minus 1 and then greater than equal to 0, and that also I will put minus 1 greater than equal to type 0. Okay. So, I can write, and range for this x and y is between 0 and 1, that means x lower limit of x is 0 and upper limit of x is 1, lower limit of y is 0 and upper limit of x is 1. So, if I use NSGA 2, so I should get this particular Pareto optimal form. Okay. So, now we will solve all these 4 problems. So, here we have to define the objective function. As you have seen, this objective function should be minimization type. Okay. So, both f1, f2, f3 whatever you have actually. So, it should be minimization type objective function, and constraints should be greater than type, that means z1 should be greater than equal to 0 and z2 should be greater than equal to 0. So, if your constraint is less than equal to type, then you have to convert it to greater than equal to type, and similarly if your objective function is a maximization type objective function, then you have to convert it to minimization type objective function. Okay. So, that we will do. So, in this particular problem whatever we have considered, so we have considered 4 problems, and objective function of these problems are minimization type and constraints are greater than equality type constraints. So, let us open R and solve all these 4 problems. So, now I will solve the problem 1. So, as you have seen, so it has 2 objective functions, that is minimization type, that is f1 equal to x and f2 equal to 1 plus y square minus x minus a sin b by x. Value of a is 0.2 and value of b is 1, and range for x is between range for x is 0 and 1 and range for y is -2 plus 2. Okay. So, let us solve this problem using R. So, I have already opened these R's. So, let us open the file. So, I would like to open a new file. Okay. So, this is your R script, and so what I have to do here. So, I have to use NSGA II R package. So, if you have not installed it, so you have to install it. So, install package, and package name is NSGA II R. Okay. So, this is the package you have to install. So, if it is not installed, but in my case it is already installed in my computer. So, I will not install it. So, what I will do, I will use the library. So, the library name is NSGA II R. So, let me execute this thing. So, I have used the NSGA II R. Now, in this case, what first we have to write? We have to write the objective function. So, objective function are, there are two objective function as I said. So, you please let us write the objective function. So, this is obj, I am writing obj fun. So, this is the name of the objective function, I am just putting it. So, this is a function, okay, function of x, and it has two objective functions. So, that is f1. So, f1 is x1, okay, and we have f2 is, that is -1 plus y, that means x2 square, minus x1, okay, then minus a sine, that is, sorry, this is a star sine. So, yes, this is b star pi star x1. Okay. So, here we have to define what is the value of a and b. So, I can define that a is 0.2 and b is 1. Okay. So, 1.0. Okay. So, this you have to define, because I am using a and b here. So, let us check it. So, this is -1, f2 equal to f. So, let us check f1 equal to x1, okay, that is your x, and f2 is -1 plus y square. Y square means here I am writing x2 square minus x1 minus a sine, a into sine b pi x. So, x1. Okay. So, this is my objective function, and then I have to return these two. So, return so R bind. So, I have to return both f1 and f2. So, f1 and f2. So, I am writing the objective function. So, here I have defined objective function 1 and objective function 2. So, both are minimization type. Now, what I have to do? I have to use NSGA II. Okay. So, you can check, you can go to help, okay, help NSGA II. Okay. So, let me check. So, this is NSGA II. So, this is the NSGA II function. So, I will use this one. So, what I will do, I will copy this one. Okay. So, here the function name is, in this case, objective function, obj, in our case objective function. The how many objective function we have? That 2. Then what is the dimension of this objective function? So, we have two variables. So, that is 2. So, there is no constraint here. So, I am not using constraint. So, there is no constraint, and so you need not use this one. So, by default this values is null and 0. So, I am not using this one. Then lower bound and upper bound we have to define. So, lower bound I am defining. So, I am lower bound I have to define. So, this is lower bound. So, lower bound is 0 and 2, okay, and upper bound is, so upper bound is 1 and 2. Okay. So, this is your upper bound. Okay. So, I am defining lower bound and upper bound. Okay. So, what I am doing here, I have defined objective function. So, this is the objective function, then number of functions are 2. So, f1 and f2. So, number of variables are 2, then lower bound is 0 and 2, sorry, lower bound is 0 and -1 -2, and upper bound is 1 and 2. So, upper bound is 1 and 2, and you can define population size, generation, crossover probability. So, other things you can define, but I am not defining here. So, I will use the default value. So, I can change it these values, but I will use the default value. So, my problem definition is over here. So, objective function I have defined. So, this is the objective function, name of the objective function is obj fun, number of functions are 2, number of variables are 2, lower bound I have defined, that is 0 and -2, upper bound I have defined, that is 1 and 2. Okay. And other things I am taking the default value. So, I hope this is fine. So, if there is no problem, I should get the solution. So, let me check. So, I have to run the objective function. So, before that I have to execute these two lines, that is a equal to 0.2 and b equal to 1, and then this is the objective function, and then this is the NSGA. I think there is some error here. Let me check what is the error. Okay. So, I think I have not defined. So, I have to define f2. Okay. So, this is f1 and f2. So, let me execute it again. Yeah. So, I am getting this solution and I can plot it or I can store it in result somewhere another variable. So, this is res. Okay. So, I am just storing it, and then if I execute this one, and then I can plot it, plot res. Okay. So, let us see, I should get the Pareto optimal font. So, here I am getting the Pareto optimal font. Sorry, I did one mistake here. So, this is +1. So, this is +1, then x2 square, that means y square, minus, so 1 plus y square minus x minus a sin b pi x. So, I hope this is correct. So, this is 1 plus y square minus x minus a sin b pi x. Now, I think this is correct. So, let me check this one. Okay. Yeah, this is correct now. So, you just see I am getting the Pareto optimal font. So, this is the Pareto optimal font I am getting. So, you can see. So, this is the Pareto optimal font here. So, I am also getting the similar Pareto optimal font. So, I can define here, this is objective function 1 in x axis and objective function 2 in y axis. So, I can define here, this is x level equal to f1 and y lab equal to f2. So, now execute this one. So, I am getting f1 and f2. So, this is f1 and this is f2 and this is the Pareto optimal font. Okay. So, I got this solution. So, as I said, so I can define the population size and other things. So, I can define here this is pop size. Okay. So, pop size is 200 and other things I can define here. So, other values. So, generation is by default it is 100. So, I can change it. Then crossover probability. So, you can change it. So, these are the other parameters, so that you can change it from here. Okay. And so, I can run it again with population size of 200 now, or make it 400. Yeah. So, you just see now there are more your population on the Pareto optimal fawn. So, what will happen if I put only 20? Okay. So, you will see that there are less solution on the Pareto optimal fawn. Okay. Yeah. So, you just see there are few solution. So, if I increase my population size, so I will get I will get the enter I will get more population on this fawn. So, I am getting this one. Now, let us solve the second problem. So, in the second problem we have three objective functions. So, here we have defined this objective function 1, objective function 2 and objective function 3, and x y is varying between -3 and +3, and I should get this Pareto optimal fawn. So, let me go to R again. So, I have already done this problem. So, let me open that one. Let me open the second problem. So, this is I have written NSGA II, and just let me open it. Okay. So, here let me define this one. So, here NSGA II anyway. So, we need it. So, if you have not installed, you please install it, and to plot it, because this is a 3-dimensional plot, means we will get a 3-dimensional plot. So, therefore, I have installed plot 3D. So, that is also required, and then I need library anyway after installation. So, you have to include this library. So, let me include this library NSGA II R and plot 3D. So, here I have defined the objective function here. So, in the objective function, so we have total 3 objective function, that is f1, f2 and f3. So, I have written here. So, f1 equal to 0.5 into x1 square plus x2 square plus sine within sine x square x1 square plus x2 square, and similarly f2 equal to -3 x1 minus 2 x2 plus 4 whole square divided by 8 plus x1 minus x2 plus 1 whole square divided by 27 plus 15, and f3 is 1 by x1 square plus x2 square plus 1 minus 1.1 into exp minus x1 square plus x2 square. Okay. So, I have defined here f1, f2 and f3. So, within this, then I am returning the value of f1, f2 and f3. So, name of this function is I am giving objective obj fun, and this is 2, okay, the second problem. So, I hope this part is clear. So, now, I have used the NSGA II. Now, this name of the objective function is obj fun c fun 2. So, objective function 2, and here we have 2 variables and 3 objective function. Okay. So, 2 and 3, that means x1 and x2 we have, and number of objective functions are 3. And generation I have used 150, population size 100, and define lower bound. So, lower bound is -3 and +3, and upper bound is 3 and 3. So, if I execute this one, so I will be executing NSGA II, and then I have plotted using plot 3D. So, here I have used, so this will be your RES now. So, I have used RES, okay, and this is also RES. res. Okay, res. Okay. So, then let me execute these lines. So, now let me execute this objective function. Okay. Yeah, and then NSGA 2, and then once I am getting the NSGA 2. So, let me plot the Pareto optimal form using plot 0.3D. Okay. So, I am using, so you just see, so I am getting this Pareto optimal form. So, this is a 3-dimensional plot. So, therefore, I have used 0.3D and which is available under plot 3D package. So, I am getting the solution. So, you can see it. So, this is a 3D plot. So, here it is F1, F2 and F3. So, I am getting this Pareto optimal font of this particular problem. So, I hope this is clear to you. So, I can also use the fourth objective function. So, F1, F2, F3, F4 or any other objective function you have. Actually, NSGA 2 is capable of taking more than 2 objective functions. So, I can use it, but here I have used up to 3, that is third objective function. So, that I can plot the Pareto optimal form. You can also solve a problem having more than 3 objective functions. So, what you have to do in the objective function, you have to write the another function. Suppose I have 4th objective function. So, what I will do, so I will write F3 here. So, okay, so F3 F4 here. Okay, so I will define that one, and then I have to return F4 here. So, you can try with another objective function, but in this particular problem we have considered 3 objective functions. So, I hope this is clear. So, let me solve the next problem. So, as I said, the third problem is constraint multi-objective optimization problem. So, we have 2 objective functions, that is F1 and F2, and then we have 2 constraints, that is G1 and G2, and please note that. So, these constraints should be greater than equality type. Okay. So, therefore, what I am doing here, I am defining G1 which is y plus 9x minus 6 and G2 is minus y plus 9x minus 1. Okay. So, I will define that one and let us see. So, go to R. So, I would like to close it. Let us open a new R script. So, here I am because NSGA 2 is already there. So, I will use library only. NSGA 2 R. So, what you have to define? You have to define objective function. So, objective function. So, in this case this is 3 and this is a function of x, and so how many objective functions we have? So, we have 2 objective function, that is f1 equal to x1 and we have f2 equal to 1 plus x2 divided by x1. So, you can see there are 2 objective functions f1. So, f1 equal to x and f2 equal to 1 plus y by x, that means 1 plus x2 by x1. So, I have defined 1 plus x2 by x1 and f1 equal to x1. So, I have defined, then I have to return this thing. So, return R bind, this is f1 and f2. I hope this is clear. So, now I have to define con function. So, con function 3 here. So, this should be function of x. So, we have 2 constraints, that is your G1. So, what is G1? G1 is x2 plus 9 star x1 minus 6. Okay. So, x2 plus 9 x1 minus 6. So, you can see that is y plus 9 x minus 6, okay, y plus 9x minus 6. So, I have defined here this is y plus 9x minus 6, and similarly I can define z 2. So, z 2 is minus x 2 plus 9 star x 1 minus 1. Okay. So, x 2 minus x 2 plus 9 x 1 minus 1. So, you can see that is minus y plus 9 x minus 1. So, this is minus y plus 9 x minus 1. So, I have to return this one. So, return Arbine I am using, and this is z 1 and z 2. So, please note that I have already explained that. Please note that this objective function should be greater than equality type objective function. So, greater than equality type objective function. If your objective function is less than equality type, so you have to convert it to greater than equality type by multiplying by minus 1. So, I have defined objective function and then I have defined constraint. So, now I can use NSGA II. Okay. So, I am using, so result I will put NSGA to output in this result variable. So, this is NSGA II. Okay. So, here this is f, then 2 variables, 2 objective function, then lower bound equal to 0.01 and 0, and upper bound equal to 1 and 5. So, 1 and 5 are the upper bound. Then I have to define constraints equal to z, and constraint dimension is 2. 2 means there are 2 constraints. Okay. So, population is 100, by default generation is 100. So, I am not defining. So, I have used the default value. Okay. So, I hope this is fine. So, if it is fine, then I should get the solution. So, let me run this particular function NSGA II. Okay. So, the name of the constraint function is confun3. So, this is not z. So, this is confun3. I hope this is fine, and objective function is not f. So, objective function is objective function 3. Okay. So, let me define that one, objective function 3 and constant function 3. I hope this is fine now. So, let me, so I did not execute this confun. Okay. So, let me execute this one. Okay. So, now execute this, yeah. So, I am getting the solution. So, I can plot it. So, this is the plot I am using RES. Okay. So, you can see, yeah. So, I am getting this solution. So, here I can define that x lab equal to f 1 and y lab equal to f 2. Okay. So, I am getting the constraint solution of this problem. So, you can see, so this is the Pareto optimal form, constraint Pareto optimal form, and this is your f 1 and f 2. So, I can also find out unconstrained one. So, let me suppose if I do not consider the constraint. So, what I will do is basically this is not required. Okay. The unconstrained one, I would like to solve the unconstrained one. Okay. So, this is result unconstrained, you see. you can say unconstrained. So, let me execute this one and let me plot this. So, I can copy and plot it. So, if I execute this one, then I should get the unconstrained solution of this problem. This is RES, this is RES unconstrained. Okay. So, let me plot it. Yeah. So, I am getting the unconstrained Pareto optimal font of this particular problem. So, this is the Pareto optimal font for the unconstrained one, and as you have seen, so this is for the constrained one. So, this solution is for the constrained one and this is for the unconstrained one. If you have more than two constraints, so that also you can use. Suppose you have another one, so I can write Z3 then Z4. So, all the constraint I can define here, and similarly if I have more objective function, so I can define all these objective function. Okay. So, I hope this is clear to you. So, how we can handle constraint multi objective optimization problem. So, only thing you please note that these constraints are greater than equality type constraints. Now, let us solve the fourth problem. So, let me open the file. So, already I did the R coding of this particular problem. So, this is the fourth one. So, here what I need NSGA II R, and we have two objective function, that is f1 and f2. So, I think this is clear to you. So, let me close this thing. Okay. And the constraint, for calculating constraint, so what you have to do? You have to calculate the objective function also. So, therefore, in the conf1 itself, so I am also calculating what is the objective function value, and then I am defining the constraint, that is Z1 and Z2. So, you can see, then after that I am returning Z1 and Z2. Okay. Then I have used NSGA II. So, here this is the objective function. So, we have two variable, two function, generation I have used 500 here, lower bound is 0 0, upper bound is 1 1, constraint is your conf1 here, and number of constraints are 2. So, I am defining here. So, let me execute this one. So, library is already there. So, I will execute objective function, then constraint function, then let me run NSGA II, okay, and then plot the results. Okay. So, I am getting, so this is the constraint solution of this particular problem. So, constraint Pareto optimal font of this problem. I can also obtain the unconstrained one. So, let me check what is the unconstrained one here. So, this is I am writing unconstrained. So, you see. Okay. So, here I will not define, yeah. So, this is not required, and I would like to plot the unconstrained one. So, this is you see. Okay. So, let me execute this one. So, this is the unconstrained one, and then let me plot it. Okay, this one. Yeah. So, this is the unconstrained Pareto optimal font of this problem. So, this is the unconstrained one and this is your constrained one. So, I hope this is clear to you. So, now you can apply NSGA II algorithm for solving multi objective constraint or unconstrained optimization problem. So, you can find out the Pareto optimal font of multi objective problem. So, as I said, so I can have any number of constraint, any number of objective functions. So, I can use, but it will be difficult to plot after 3. So, after 3 objective function. So, let me stop here. Thank you very much.